I'm Hyoritsuji from Keio University in Japan. I will be presenting a paper titled CradlePosture, camera-based approach for estimating neonates' posture based on caregivers' holding behaviors. As a background, caregivers often engage in holding behavior to soothe crying infants. This kind of early positive physical interaction is considered important for both caregivers and infants. For example, physical contact during holding behaviors is believed to have long-term effects on caregiver sensitivity, infant self-regulation, and the bond between caregivers and infants. Additionally, a neonate's posture during holding is directly linked to their safety, so caregivers need to learn proper holding techniques. However, opportunities to learn these techniques from experts are mostly available in professional environments, such as hospitals. This gap highlights the need for a system that enables easy training of holding techniques at home or in non-professional settings. Training methods differ before and after a child is born. As a prenatal training, caregivers can use baby simulators to evaluate their holding techniques and receive feedback. Another approach involves attaching a smartphone to a stuffed animal to assess and provide feedback on holding techniques, which does not require specialized equipment. After a baby is born, there is a higher demand for evaluating holding techniques with actual neonates rather than simulators or stuffed animals. Therefore, for postnatal training, a system that can monitor and analyze a neonate's posture during holding and provide feedback to caregivers is essential. Developing such a system requires the measurement of neonate posture. So, our purpose is to estimate neonate posture angles during holding without attaching sensors directly to neonates. A simple method for measuring posture involves directly attaching sensors to the baby, but this approach may lead to resistance from caregivers and impose a burden on neonates. A method for estimating posture without touching sensors is a camera-based approach. One uses CNN for feature extraction and estimate posture based on spatial-temporal relationship. Additionally, many studies utilize MediaPipe, an open-source tool that can perform pose estimation. They validated the concurrent accuracy of posture estimation of MediaPipe compared to IMU measurement, and reported a strong correlation between them. However, since these models are based on adult posture data, their accuracy is limited when applied to neonatal posture measurement. In research focusing on infant movements and posture, the study on the left proposed a model that captured infant motion and shape from RGBD data. The study in the middle extracted motion information using optical flow. The study on the right expanded OpenPose, that is a pose estimation algorithm, to handle infant postures. However, these studies require capturing the infant's entire body and focusing on infants in a lying down posture, so they don't address posture during holding. Therefore, we propose a camera-based approach for estimating neonate's posture based on the caregiver's holding behaviors. Our method is based on the idea that the neonate posture changes depending on how a caregiver uses their arms and shoulders when holding the baby. In this study, we focused on the cradle hold, a basic method of holding a neonate, as shown in this figure. To simulate a neonate, we used a baby doll with the same weight and shape of a real neonate. We employed media pipe pose to capture the caregiver's holding movements and X sensor attached to the doll's chest to measure the neonate's posture angles. Here is an overview of the system used in our research. First, we recorded videos and measured the posture angles. Then, we processed the video using media pipe pose to estimate the caregiver's posture and detect landmarks. Using the landmark coordinates, we developed a regression model to estimate the posture angles. This study focused on estimating two angles, the inclination angle and the adduction angle as a figure. The inclination angle was chosen because it reflects the movement of lifting the baby's head. Then, adduction angle was selected based on studies suggesting that tilting the baby's body sideways can help calm the baby. To create the model, we began by collecting data. We synchronized the data recordings and X-sensed measurements. Each participant completed two 30-second trials. In the first trial, they gradually changed the inclination angle as a video, and in the second trial, they gradually changed the adduction angle. Next, I will explain the preprocessing and model construction. For angle data, to standardize the data distribution across participants, 140 data were randomly selected at 10-degree intervals within the 0 to 40-degree range. Then, for video data, the absolute coordinates of the 25 upper body landmarks obtained from media pipe pose were converted into relative coordinates using the midpoint of both shoulders as the origin to account for changes in coordinates values caused by the participant movements and camera shake. We employed a random forest regressor to construct the models, with the posture angles as the responsible variables and the landmark coordinates as the explanatory variables. Then, we conducted within participant and between participant validation. For within participant validation, we developed models for each of the 5 participants and performed 5-fold cross-validation. For the between participant validation, we performed cross-validation by using one participant's data for testing and the other for participants' data for training. As a result, the within participant validation shows high accuracy for the estimation models. Coefficient of determination were 0.9 or higher for all participants, except for the P1 adduction angle model. Since the participants' own data for both training and testing were used to construct the models, we were able to capture individual patterns of motion for each participant. On the other hand, for the between participant validation, we observed that while the inclination angle could be estimated, the adduction angle could not. A possible reason for the difficulty in estimating the adduction angle is the camera placement. It was positioned in front of the participants, making it hard to capture arm movements involving depth. Additionally, the decrease in accuracy may be attributed to variations in motion patterns among participants, making it difficult to create models that are universally applicable to all. In future research, we aim to not only improve accuracy but also investigate the acceptable range of estimation errors. Finally, regarding limitations and future work. In this research, the range of angle estimation is limited to 0 to 40 degrees, but I would like to be able to support a wider range of angles. Expanding this range requires more precise instruction to participants during data collection to ensure consistent movements. Additionally, in between participant validation, the estimation accuracy for the adduction angle was low. This suggests that incorporating side view camera information would be necessary for improvement. Moreover, this study focused on the cradle hold, the basic way of holding neonates. However, as holding styles change with developmental stages, building models for other holding is also essential. In terms of practical application, we have not validated whether this method works when holding an actual neonate. There could be significant errors in posture estimation due to the neonate's movements. Furthermore, based on the results, creating a personal model is necessary to develop an accurate feedback system. This means users must collect their own data, which is time-consuming. Therefore, we aim to improve between participant validation and make the system applicable to untrained users to reduce their boredom. Here is a summary of my research. Thank you for listening.